Okay, good afternoon. So my name is Shiva. I'm a Technical Outreach Manager at EGI.eu, the coordinating institute of the European Grid Infrastructure Collaboration. And in the next roughly 60 minutes, I'm going to talk about the services that EGI can offer to the chemistry, molecular and material sciences and technology community. This talk is in the context of the virtual team project that we are having with you inside the EGI collaboration, and this project is titled Towards a CMMST Virtual Research Community. This project runs for roughly 6 months with the aim to define a framework for a virtual research community from this scientific discipline, which we call here computational chemistry, molecular and material sciences. Just to recap a little bit on the purpose of having a virtual research community in EGI. These communities represent a specific scientific group from the European research area inside EGI. Those like-minded scientists, technologists, software developers, software operators who have worked together in that particular scientific discipline and represent the users of that scientific field inside the EGI collaboration. A VRC is formalized through a Memorandum of Understanding with EGI, and such a Memorandum of Understanding is a few page-long document that roughly defines the resources that are consumed or needed from the different EGI member states, the national grid initiatives. It defines the joint activity areas on which this VRC and the rest of the EGI community works together. It can be development of new software, operation of software, community-specific events, community-specific support services, and so on and so forth, and defines communication channels between EGI and between that scientific domain. In this virtual team project, we try to define the structure of such a virtual research community in the computational chemistry and material sciences domain, and that means that we need to define the structure, the organization and funding model structure for the VRC itself, how that VRC links to the community, to the EGI community, the named contact points. We need to define the technologies, resources, and services that are already exist in EGI and should be allocated for this new VRC in order to work effectively, and identify technologies and services that don't exist at the moment in EGI and should be brought into EGI by this VRC or by any other members of EGI in order to facilitate the efficient work of this computational and material sciences community. So the outcome of this virtual team project that runs for 6 months should be a proposal on how to establish this virtual research community inside EGI. And what this talk today aims to clarify is a little bit on what EGI can offer for this virtual research community, and hopefully through this, you as the listeners of this talk will have a better understanding also of what isn't available in EGI and what should be developed in EGI or inside your community in order to link your services and your people to EGI efficiently. So the content of this presentation directly relates to point and objective number 2 and number 3 of this virtual team project. And in this roughly 1 hour long talk, I will just go a little bit of background information on EGI, who are the main stakeholders, who are the main users, and what are the strategic activity areas we are working in. And then spend most of the time on specific services that are facing scientific communities and that we can offer for the CMMST community as well. And in this detailed second section of the presentation, I will focus on those, mainly on those technical areas that you flagged to me as high important and priority topics for this community, particularly the user support structure, ready-to-use scientific applications, grid and cloud infrastructures, and collaborative services that can help your community to get more organized and better structured. And also we'll spend quite a lot of time on workflow integration and scientific gateway tools and frameworks that are available in EGI for this community. And at the end, I will just briefly talk about another new initiative that is relevant for the CMMST community, namely the HPC and the HTC integration activities that are ongoing inside EGI. So the European Grid Infrastructure Collaboration started in 2010 after a decade-long series of projects invested in by the European Commission. In 2010, over 35 countries established this European grid infrastructure by bringing together computers, data, and applications. And as you will see from the presentation, many more aspects such as the human support services, high-level tools and services for the benefit of the European research area. The goal of this collaboration is to provide an IT infrastructure that enables the secure sharing of computing data and application resources for scientific simulations and visualization purposes. The key activity that this European Grid Infrastructure Collaboration does is provisioning of this multinational infrastructure, which is currently the largest multinational grid of the world. Most of the clusters and data repositories and services that are located in this European grid infrastructure are contributed from national grid infrastructures, mostly from Europe, but also we have partnerships with resource centers in the USA, in South America, and the Asia Pacific region. And some of the latest statistics from March shows that more than 300 resource centers are providing computing and data capabilities in the infrastructure, with more than 370,000 CPU cores and a large number of disk and tape-based storage resources. However, this large amount of capacity is not available for any single community. Communities can have a subset of these resources based on some resource allocation policies, and this resource allocation policy enables us to structure this large infrastructure for what we call virtual organizations and virtual research communities. I talked in the introduction about virtual research community. It's a group of like-minded scientists and their support people, technical people, organizational manager people who work from a scientific area and need to use European grid infrastructure services in order to conduct and facilitate their research agenda. These research communities can establish what we call virtual organizations on the physical infrastructure that EGI provides. A virtual organization, as you can see on this slide, is a group of users and a group of sites that support those users in order to conduct their research. These sites provide data and computing capacities for the users, and through some coordinated access mechanisms, the users can access the resources from the VOs that they are members of. Here in the left side still, you can see that actually some of the VOs belong to a specific virtual research community, but some of the VOs, for example, this VO in the right, doesn't belong to any virtual research community. So it's also possible to have virtual organizations that are not linked to a larger structure, the virtual research community, which is a more flexible structure. That's why I use the dotted line here. It indicates that it is a more fuzzy boundary of where a virtual research community ends. In case of a VO, it's quite well defined. We know the number of sites, exactly which sites support a particular virtual organization, and we know exactly who are the members of those virtual organizations. And here you can see that there are actually two types of VOs. There are cloud-based VOs and there are grid-based VOs. I will talk about that later, but here the only important information is that a virtual organization provides computing and data capacities for a set of users. On the right side of the slide, you can see what are the current virtual research communities that exist in EGI and what are the most active VO groups. Activity here is defined by the amount of CPU hours that these virtual organizations use from the grid infrastructure or cloud infrastructure. This slide number 7 aims to clarify a few terminologies that someone easily runs into when starts working with EGI. And sometimes these can be a bit problematic to remember. What's the difference between three items? One is EGI, one is EGI.EU, and the third is EGI Inspire. So really this slide just tries to clarify the differences between these three terms. First, EGI is the broadest term. It refers to a collaboration, an ecosystem that incorporates infrastructure providers, resource providers, technology providers, software developers, and users of those systems. The EGI.EU refers to an organization based in Amsterdam with 20 people. That's where I work, which is as a legal entity registered as a Dutch foundation and is responsible for the coordination of the work of the European grid infrastructure collaboration. We are the one who bring in new operational solutions, bring in new technologies, and facilitate the interaction with new user communities, such as this time with the computational and material sciences community. And the third term is the EGI Inspire, which is the name of an SP7 project, which runs for 4 years, started in 2010 in May, just when EGI was started. And the goal of this 4-year-long project is to move the EGI collaboration towards a sustainable structure, which means that the operation of the European grid infrastructure becomes independent from FP7 or FP8 funding project sources. So let's move on a little bit about talking about the main stakeholders of EGI, and they are the national grid initiatives, or NGIs in short. An NGI is a country's single point of contact for governmental, research community, and research centers as regards its participation in the EGI collaboration. NGIs are the main providers of computing and data capacities, as well as different types of support services. The most important support service in this respect for you is the user support contact. Every NGI has 3 types of support points. One is the international liaison, the second is the user support point, and the third is the operational infrastructure support point. And this user support point is accessible on the EGI website and at the link which is in the title of this slide. If you click on this support link in the middle of the page, you will get an interactive map where you can pick the user support contact of any of the EGI member countries. And then typically what you get, this slide shows an example of Switzerland, that you get the support entry portal, you get a contact email list, and you get a description of the main activities of that national grid infrastructure. But the NGIs are not the only contributors of EGI. They are the most important one, but not the only one. On this slide, I will collect all the different types of contributors of EGI. These can be classified into 2 groups. One is the legal entities, and one are the projects. The contribution that legal entities and projects put into EGI are formalized with Memorandum of Understanding and Service Level Agreement. So with each of these entities, we have either an MOU or an SLA or both. On the legal entities side, we have EGI.EU as the coordinator of the whole collaboration. We have national grid infrastructures, and we have European Intergovernmental Research Organization, particularly CERN and the European Bioinformatics Institute. And on the project side, we have EGI Inspire as the key project that drives EGI towards sustainability. But we have another large number of projects that provide specific support or specific services in the collaboration. And these projects can be classified as grid and cloud technology providers. These are the projects that develop grid and cloud middleware technologies, software technologies that are deployed across the infrastructure in order to provide the integrated uniform access mechanisms for users. The high-level technology projects, such as Shiva, Shiva, and Mapper, are providing higher-level software technologies that are specific to certain use cases or certain workflows or gateways. The science domain-specific projects provide high-level services that are specific to a certain scientific discipline and specialized for the niche needs of those scientists that are working in that field. So projects such as Chain and EUDAT try to link in resources from new regions or new types of resources into the EGI infrastructure. So on slide number 10, I'm showing you the 3 key strategic focus areas that EGI has. The core business of EGI is operating an infrastructure. We have a well-established grid infrastructure which was developed over the last decade or so, and which is heavily used by various scientific communities. Recently, we started building a federated cloud infrastructure which aims to provide more flexibility and new types of access mechanisms for scientific communities. I will talk about these 2 infrastructures in a minute. Just operating an infrastructure isn't enough. The point of having an infrastructure is that it can be used by scientific groups for their domain-specific sciences, use cases, workflows, and so on and so forth. So we need to facilitate the integration and operation of scientific environments with this operational infrastructure. So another key strategic focus area of EGI is working with scientific groups and facilitate the integration of their domain-specific services with the operational infrastructure. And all this requires community and coordination activities that governs the operation of the infrastructure, that governs the linkage of new types of services and scientific environments, and that provides an in-reach and outreach communication mechanisms so we can effectively communicate about the services we provide or we wish to integrate. And in this presentation, in the rest of the presentation, I will focus on the virtual research environment integration activities, because that's important for a domain-specific group, such as the computational chemistry. And I will talk a bit about the community and coordination activities that we can provide for this new VRC. So in these 2 domains, what are the services that we can provide for a research community in general? Research communities are very different. That's what we learned over the last couple of years. But we see a common pattern. The common pattern is that every research community has kind of different layers. The thickest layer is the kind of individual researchers who work mostly alone and need high performance computing or high throughput computing capacities in order to implement the applications, the models, the algorithms that facilitate their personal research workflows and research agendas. Sometimes these users are grouped into smaller research collaborations, maybe at the institutional level, sometimes at national level or at international levels, and they want to carry out simulations using supercomputers, clusters, large data capacities in that research collaboration together. So these research collaborations, such as the life sciences grid community, the VNMR community, or the agronomical sciences AG infra community, or the seismological community, for example, the VRCHA. These are just 4 examples that I put there that we work together with at that level. Some communities are aiming for even more and would like to define services that are very specific for their domain and want to operate those services efficiently for for multinational scientific groups. These are typically the research infrastructures that want to set up a large number of services, a large service portfolio that is linked to the European grid infrastructure or other distributed computing infrastructure and operate those services efficiently. And recently in Europe, there is an even higher layer. On this slide, it's the bottom, so it's the lower layer, which are the research infrastructure clusters, basically projects that group together a number of research infrastructures from the same or related scientific fields and try to find synergies in the services of those research infrastructures in order to exchange best practices and in order to facilitate the setup of those services centrally among multiple research infrastructures. And these, no matter which scientific or research community we are talking about, we can see this layering inside. And what the layering means is that basically slightly different types of services or needs emerge at the different layers. While individual researcher and research collaborations are trying to use services that are out there. They don't want to invest too much into the setup, into operation of services. Larger collaboration want to create new services, want to enable new type of applications on a distributed computing infrastructure, or even more, they want to operate services for their customers. And EGI need to be able to provide services at all the three levels, even for those who want to use ready-to-use services, to those who want to develop new services on top of a distributed computing infrastructure, and to those who want to operate a large service portfolio for a well-defined scientific discipline. And to meet these demands, EGI offers basically 5 types of services. The first, for those who just want to use services, we have scientific applications that are already integrated with EGI and are available through portal interfaces, command line interfaces for anyone to reuse. For those communities or those members of a scientific community who want to create new services, we provide grid and cloud, recently cloud capacities in order to set up and create new services, to run their own custom simulations, their custom workflows. And to facilitate this work, we also provide high-level tools, application porting, and application hosting environments that could be used in order to simplify the integration of new application and the creation of new services. And for research infrastructures, for multinational collaborations, we offer services that help them get organized, collaboration and communication services, and we provide services that help them operate a multinational infrastructure, operate a complex network of services for third-party users. In this respect, we provide operational tools and dashboard systems that help the operators of those services to monitor performance and availability and accounting and so forth. So the big question that the virtual team project need to answer is, what's the structure of the CMMST community? How these 4 layers appear? Are there 4 layers or are there slightly different layers? What are the key players at the different layers? This is basically what the first objective of the virtual team project is, to define the structure of the CMMST virtual research community. And the second key question is, what are the services that the CMMST virtual research community wants to use in EGI? Or in other words, what this community wants to achieve with EGI in EGI. And the virtual team project second and third objectives tries to answer that question. So in the rest of the presentation, I'm going to go into technical details about the 5 topics I have in the middle of the slides. And in the title of the slides, I will give you the number about which I'm talking about. So I will go from 1 to 5. The first is scientific applications that are already integrated with EGI and could be used by any of the existing or any new community. These scientific applications are registered in an application database, which is a registry where one can browse applications from different perspectives. The most important for you is that it can be browsed by scientific discipline. So if you go to this fdb.egi.eu page and click on the left side, the browse graphically by discipline button, then you will see a page like that where the different disciplines are displayed on a pie chart. And if you choose computational chemistry, you will see that it includes 33 items. And if you click on that slice of the pie, then you will get a listing of those 33 items that are already registered in the EGI application database. And if you click any of the items, then you will get a detailed profile about that particular software entry, which will be a short description of what that software is for, how to access it, whether it's a portal-based access or whether it needs download to the client side, whether it needs registration in a particular virtual organization in order to use it, and so on and so forth. What you can also do is, even if you don't use the application, you can still interact with the application. You can register for updates to receive updates about changes concerning that application. This can be in an RSS or Atom feed based update. You can provide rating or feedback or comments on particular software entries. And with each software entry, there is a set of providers or supporters associated with, so you can send direct messages to those people in order to need clarification about the application or in order to want to send direct feedback to them in a personal message. So I don't have a detailed view of the 33 items here. I welcome you to go to this website, to browse the 33 entries that are here, to take a look at how relevant those are for the virtual research community and which of these applications can be used in the virtual research community. If I'm not mistaken, that's one of the activities in the virtual team project, and if I'm not mistaken, it's Yelena who is leading that activity. The second area, or the second set of services we can provide, is the capacity, the computing and data capacity that are provided by the resource centers of EGI. And I have different slides about the grid type of accessing those services and about the cloud type of accessing those services. First, let's talk about the grid type of access. These grid services are operated on the different resource centers, on roughly 350 resource centers. And basically what's available on those centers is the grid middleware called UMD, Unified Middleware Distribution. It's a complex software stack that incorporates contributions from G-Lite, Arc, Unicode, EK, Saga, and desktop grid middleware types. And all these services in this Unified Middleware Distribution provide batch, job submission, data transfer, metadata management, and access control services for virtual research communities. And once, if someone wants to use and access those services, then needs to register in a virtual organization or set up a new virtual organization and get access to some of the resource capacities through this new VO. And once that's done, can define domain-specific application and perform domain-specific computing and data transformation. There are already computational chemistry-related virtual organizations in EGI. I just checked the latest statistics. There are 2 global virtual organizations. By global, I mean that the contributors, the sites who support the VO, are from multiple countries, and it accepts users from anywhere. There is one VO called ComCam, and that's the website of that VO. It is in Perugia, so Antonio is managing that VO with his colleagues, and there is one called Gaussian, which is managed from Poland. Besides these two multinational or global VOs, we have national computational chemistry VOs in Portugal and Spain, and we have a large number of regional and multidisciplinary VOs that are not dedicated for computational chemistry, but could be used by anyone, including the computational chemistry community. And if the virtual research community would like to set up a new virtual organization, it can do so by going to this website in the operations portal and register the new VO. And once that registration is done, it will trigger a request to all the sites, all the 350 sites of EGI, of getting support for the VO. And those countries and those sites that have a priority for supporting computational chemistry science can join the VO and donate resources for this virtual organization. I have a couple of animated slides now of going through what you can use a grid-based virtual organization for. I show these usages in two use case examples. The first use case example is the batch processing, which is motivated by a user who needs to use EGI grid sites in order to perform a compute-intensive simulation. In this respect, we have the user in the left side, we have the sites that support her video on the right side, and as you can see, each site includes a storage service and includes a computing service. And possibly on the storage service, there are some files that the user wants to process. These files could be placed onto the storage by the same user or by other members of the same virtual organization. So as the first step, the user goes to a user environment, which can be a command line, which can be a portal-based environment, and authenticates herself, basically logging into the grid using a virtual organization management service, identifying herself so the grid will know that she actually belongs to that virtual organization and can access the data and the computing resources of the VO. Then defines her computation in terms of batch computing jobs and submit these jobs to a broker service. Typically, this submission includes the smaller input parameters to drive the computation. Meanwhile, the large input files or input data is located on storage services and are not transferred from the user environment to the broker. The broker uses an information system to identify which are the most suitable sites of the virtual organization for the computing. Uses a logging and bookkeeping service to make record of this selection and then submits the jobs onto the different computing sites. The jobs can start up as batch computing processes, can read and write files in the different storages of the VO. And once the jobs are finished, the job status are logged, recognized by the broker service, recognized by the user, and then the final output are retrieved and picked up by the user through the user environment. Typically, again, only small files are transferred from the sites to the user environment, and large files stays in the grid on storage services. And to show a particular example of how this use case is applied, I took an example for the Pierre-Auger collaboration, which is an astronomical collaboration, which deals with data that is generated at two observatories, one in the US and one in Argentina. And these two large satellites are producing data that is transferred to a French storage service at CCNI2P3. And this French storage service stores the cosmic ray files. The central information service, VO management services, central logging and bookkeeping services are provided for this virtual organization, the Auger virtual organization, by a Czech partner. And then the Auger collaboration develops software and distributes software centrally to its users in order to perform computation that can make sense of the cosmic ray data. So the users use the centrally distributed software to define custom interpreters of the data and to perform compute-intensive simulations using the cosmic ray files. These jobs are submitted to the different sites that support the VO, pick up the input data from the French side, write output data there, and write output data back to the user environment. And the second use case that the grid virtual organizations of EGI could be used for is what I call here data and metadata management. And this use case is dominated by the use of large-scale data and the use of metadata in order to index the different data elements, the pieces of data, and to make queries and searches that use the metadata. So the situation is the same as earlier. There is the user environment, there is the virtual organization, which includes several sites, each with its own computing and storage services. There is an information system that knows about the status of these sites. The VO management service is used first to log in. And then in this scenario, what the user does is basically to upload files and download files between the user environment and the storage service and register these files in a file catalog or in a metadata catalog. The file catalog provides a user-friendly name for the files, so the user can see the distributed storage services as a single hierarchy or directory hierarchy, doesn't see the fragmentation and the physical location of the files across Europe. And the metadata catalog can be used to associate some tags or user-friendly parameters with each of the data elements, in this case, for example, with files. So the user can look up, for example, files based on the date of an experiment, based on the users who were involved in the experiment, based on any particular parameter that the user finds interesting and relevant for the data lookup and the data registration. So meanwhile, file content is stored in physical files on different storage services across the VO. The metadata and the file catalog data that is stored in centralized registries is accessed by the user centrally in order to do tag-based lookups and more intelligent searches. A particular implementation of this use case is, for example, the G library environment, which provides a digital repository of the digitalized work of Roberto, who was an Italian poet from the 19th, early 20th century from Naples, and whose work is originally on very old papers that are very close to be destroyed. So the local digital heritage community, preservation community, digitalized these old papers and created large size TIFF and PDF files, which are 3 terabytes in total, and put these files onto storage elements of a dedicated virtual organization. The files can be even replicated, so multiple copies of the same file can be stored on different storage sites in order to provide fault tolerance or scalability. And after the files are copied onto the storages, the references are registered in a file catalog called LFC and in a metadata catalog called AMGA. And based on these file catalog and metadata catalog entries, the users who log into a web portal can search the work and browse the work of Roberto based on some user-friendly tags, such as the date of the publication, such as the title, such as any keyword in the content. So meanwhile, the point I'm trying to make here is that once someone gets access to an EGI virtual organization using the grid technologies, then the virtual organization resources could be used to perform batch computing, to perform data analysis, data storage. Of course, these two use cases can be mixed, so someone can use large-scale data to perform compute-intensive applications. And how to define those applications is the third topic of my talk. And in this third topic, I will talk about application porting and hosting tools that are available for EGI users and EGI user communities. These application porting and hosting tools are registered also in the EGI application database, just like ready-to-use scientific applications. These tools are grouped in various categories. For example, developer tools, frameworks and toolkits, science gateway frameworks, and workflow systems and workflow tools. And if we look at how users want to use a grid or a cloud infrastructure, then basically the domain-specific application and services that a scientific community wants to build to interact with grids or clouds have different layers. The top layer is some service access layer, very typically some web portal, or in other words, a science gateway that provides a web-based environment for the work. Below, or as part of the science gateway, there could be some workflow systems that can identify services from the underlying scientific and grid and cloud domains, can integrate those services together into multi-step operations, multi-step processing workflows, and can orchestrate those workflows using the underlying services. And only below that, there is the real domain-specific part, the really unique bit, which can be the domain-specific scientific algorithms, the scientific applications, simulation tools, databases, and workflows that are used and specific to that particular community. So the purpose of the application database is to categorize and provide visibility to those science gateways, portals, and those workflow systems that could be reused across different use cases, across different scientific communities, across different countries or regions. And that is why we are tagging and categorizing the reusable tools as science gateways and workflow systems in the application database. So depending on your needs, you can find the relevant items in the applications database. So I'm going to talk first about the workflow tools, and then after that about the science gateway tools that exist in EGI. A workflow tool is basically used to define a multi-step simulation. A workflow tool typically incorporates an environment where someone can define this multi-step simulation. In the simplest case, the environment can be just a text editor, where someone describes the simulation as a kind of program code with simple programming style text or an XML description. In more complicated cases, it can be a graphical environment that provides drag and drop facilities to create graphs that describe this multi-step simulation. What we see is that there are a large number of environments that exist around the world, not only in EGI, but around the world, to define workflows. These different environments sometimes use the same workflow language to actually describe the multi-step simulation, but very often each has its own unique workflow language. So a workflow defined in one environment can be hardly used in another environment. And after someone defines a multi-step simulation as a workflow, needs a workflow engine that can interpret that workflow description and can actually invoke services or submit jobs to a distributed computing infrastructure to carry out the work defined by the workflow. In EGI, we try to categorize and collect those workflow tools, workflow systems that are interoperable with the EGI grid and cloud systems, with the grid middleware services and with the cloud middleware services. These workflow tools are registered in the application database, and if you log in, in the left side you can see a workflows button, and if you click that, you will see the 26 workflow systems that exist in EGI at the moment. This is a very fresh screenshot. I just made it yesterday. And instead of going through all the 26 solutions, I'm just picking one which I believe is the most relevant for this computational workflow systems into an interoperable and shareable platform. You can see in the right side of this slide that the Shiva simulation platform is basically a gateway that sits between the user using a web browser or a desktop environment and a large number of workflow systems. These systems on the right side are different workflow interpreters, different workflow languages. Each of these engines is able to submit jobs or invoke services which is specific to that domain. What the Shiva platform does is that it includes adapters for each of these systems and makes these systems able to communicate each other. What this means is that using a Shiva repository, users can develop workflows and share workflows with each other, put the workflows into a central repository. Users of the same or maybe even other workflow languages can pick up these workflows, can use these workflows as what we call black boxes. So without opening the workflows, these workflows can be used as a black box where I see what should go in, what's the file format, for example, how I should define molecules, and I will see what comes out. Basically, I understand the file format that the workflow will generate. And inside the Shiva simulation platform, I can use these workflows as black boxes in order to build larger workflows, what we call here meta workflows, which are actually built from smaller workflows. So it's a workflow of workflows encapsulating black box workflows at each stage of the computation. So in this way, someone can define large-scale computation using workflows made by others, maybe written in different languages that you don't even have to know, you don't even have to be able to open, but you can just combine these into large-scale computations. And you can donate these workflows and meta workflows in a Shiva repository. So the Shiva simulation platform is provided in a portal-based interface, which is available at this website. And it was created between 2010 and 12 by a FP7 project called Shiva. And since 2012, there is another project called ERFlow, which provides dissemination and support for users of this Shiva technology platform. And within this ERFlow project, there are four communities that are already signed up for using this Shiva simulation platform: astrophysics community, heliophysics community, life sciences community, and also the computational chemistry community represented by the Technical University of Dresden and the Ludwig Maximilians University of Munich. So I welcome you to go to this website to take a look at what the computational chemistry community already using the Shiva platform for. You can browse the Shiva repository to see what workflows they are using, and you can join them in using the platform and making the workflow repository richer with additional workflows, with additional simulations that could be combined into large-scale meta workflows. Also, I would like to note that the ERFlow project is looking for new communities to support. So even though there is already a computational chemistry community inside Shiva, there could be additional communities from the same domain who become users. If you are interested, you can contact the project at that project website. And this animated slide basically just shows you a real example of how the Shiva simulation platform could be used. Here we see two users, one in the left, one in the right. They are using different workflow languages. And this can be seen from the different representation of the workflows. They are familiar with different workflow tools that have different icons and logos and everything. These workflow tools are compatible with different distributed computing infrastructures, and these workflow tools don't even see other infrastructures, don't see other types of workflows. But what the Shiva simulation platform can do is, after these workflows are shared in the Shiva repository, then through the repository and through the meta workflow developer environment in the Shiva simulation platform, the second user can discover the first user workflow and can embed that into a larger simulation and then run the two workflows together as a single stage, as a single unified application, combining different workflows, combining data from different sources, and combining the capacity of multiple distributed computing infrastructures. Okay, let's move on to the next topic, the science gateways, which is, if you remember, the highest layer of interacting with EGI services. Science gateways are actually application-specific environments that encapsulate different tools, applications, data collections, and are integrated typically into a web portal. Sometimes there are desktop-based science gateways, but those are less and less used, and the portal-based gateways are dominating largely this field. The main drivers of science gateways is that it provides simple access for users. So instead of learning the complex command line tools that are available for interacting with grid or clouds, one can just use a web browser and intuitive graphical interfaces to define and run simulations. And another driver is the modularity. So science gateways can be customized for individual groups, individual researchers. And the modularity of these gateways enable a simple customization and rearrangement of services, rearrangement of graphical elements in the interface. What we see is that scientific gateways are domain or community or sometimes user specific. However, the technologies that are used inside gateways are not. And therefore, there are so-called science gateway frameworks that facilitate the setup and the creation of new gateways using a framework that is customizable and extendable for specific needs. Inside EGI, there are two main science gateway frameworks. One is called GU's WSP grade, the other is called Catania Science Gateway Framework. These two are largely the most heavily used at the moment, and each have more than or around 20 different gateway instances that are using these. These gateway instances are specialized for different scientific domains. For example, the MOSGrid portal is a molecular simulation portal, eBioinfra portal is bioinformatics portal, dBrain portal is the life sciences portal, but sometimes are specific for a country, such as the Hellas Grid portal is the Greek National Grid Infrastructure portal. So these science gateways enable customization for specific scientific disciplines or for specific countries or regions. If you are interested in the complete list of the gateway instances that are generated from GUs, you can look at this URL, and for the gateway instances that are using Catania Science Gateway Framework, you can use and visit this page. Inside EGI, we use the application database again for categorizing and giving visibility for the Science Gateway instances and also for the Science Gateway frameworks. So if you go to the applications database and click on the Science Gateways link in the left, in the middle, then you will see that 49 instances are available at the moment in the application's database. And what is inside the Science Gateway is shown on this slide, which is titled Anatomy of a Science Gateway. What we see is that there is more or less the same pattern inside the Science Gateway, no matter which Science Gateway instance or technology we look at. On first, in the left, you can see that there are some scientific applications that are embedded into the Science Gateway. These are the applications that are specific for a community or specific to a country and do the real computation. These are the applications that could be, for example, the workflows to define a multi-stage simulation, or could be just single applications that are run as a single unit of execution. These applications are run on grids, clouds, HPC, and use external databases as they wish through some job submission engine and data transfer engine that is specific to the Science Gateway. The Science Gateway uses these two engines in order to launch the applications on the remote clusters, clouds, grids, or to transfer files and data between the Science Gateway and the remote resources. This is made accessible to users through a web interface that enables login from a web portal, and an authentication and authorization module inside the Science Gateway recognizes the user and decides what a user is allowed to do inside the gateway and through the gateway on remote resources. And typically, gateways distinguish different types of users and associate different roles to the users based on their position. The main roles are typically the administrators, who have the highest privileges, can do whatever they want in the gateway. The power users, who typically can configure applications, can create new applications in the gateway. And basic users, who are very typically can just log in and run a predefined application with their own data. So they are not allowed to upload new applications and to modify the existing application significantly. Just to show an example or two examples for this structure. The first is the molecular simulation grid portal provided by the MOSGrid project in Germany. This is a portal that provides access to HPC resources through the Unicore system. So in the right side, you can see the HPC supercomputing resources. Unicore services are making these accessible. And this portal is built with the GU's WSP grade technology, using a GU's as a job submission engine and WSP grade as the presentation layer. Plus, it also incorporates a data transfer engine from the XtremeFS file system solution. The users can log in to the portal and with certificates can authenticate themselves. The portal allocates access rights to them so they can modify and access the existing workflow applications that are from the quantum chemistry calculation domain, molecular dynamics domain, and docking domain. I'm not a chemist, so you probably know much more about these applications than I do. This is just to indicate that these are the workflows that someone can already use in this system, but the workflow editor that can be seen here enables users to define new simulations from existing applications or by uploading new applications. And different graphical interfaces that are part of the different applications make the results of the computations and simulations more consumable. So these portlets provide graphical browsing capabilities for the computing jobs or computing workflows, and also for the final outcome of the different computations. Another example of Science Gateway is the Chain Application Gateway, which can be seen as a snapshot on this slide and can be accessed at this URL. This chain project is running in order to harmonize infrastructure and applications from different regions, mostly outside of Europe, mostly in the Southern American region. What they set up was an application repository, which can be seen here, which lists all the applications that this chain project and initiative supports. And on this application repository page, one can see the name of the application, a running page for the application, what the scientific domain of the application, what grid middleware is used under the application, and which institute provides support for that application. And if someone clicks on one of the icons on the run page, then what happens is that based on the icon you choose, you will choose basically an entry point to a specific science gateways that give you a running capability for that application. In that particular science gateway, you can sign in using an identity federation, a username and password typically issued for you from your institute. So if you are from an academic institute, then you can use your academic username and password in order to log in into these science gateways that are behind this chain application portal. Typically, after you log in, you need to register for the gateway itself. So they also need you to provide some additional information on top of which institute you are from. You can do this registration only once. And once you've done this registration, you can just log in and run predefined applications with your own data. So still in the same chain science gateway project, I ordered the applications based on computational chemistry, but I found that actually, unfortunately, none of the computational chemistry applications have a running page at the moment, which means that these applications are available not through a graphical science gateway, only through command line interfaces that are outside of this science gateway world. However, I consulted with the providers of chain, and what they said is that they operate an entry point to request the integration of any of these applications or other applications with science gateways. So if you fill this survey, then they can work with you to integrate these applications with the science gateway interface. Note, however, that some of these applications are the same that are running also here in the MostGrid portal. Okay, a few words about the recent trends in science gateways. What we see in Europe is that, and specifically in EGI, is that there is more and more science gateways. Actually, the number of gateways that are established is growing, is increasing. And this is because establishing a new gateway is simpler, much simpler than it was even a year ago or 2 years ago, not talking about 5 or 10 years ago. This enables even smaller groups to set up their own gateway, which is specialized and customized for their own needs. What we see is that gateways are gaining momentum to providing integrated access to not only grid, but also to cloud resources. Sometimes this is transparent to the user, sometimes it isn't. The point is that gateways are now, many of the gateways are ready to submit jobs and manage services in clouds as well. Gateways are going into the direction that provide a transparent authentication for the users. This means that the users can use, for example, their institutional login name and passwords, sometimes even open system authentication such as Facebook or Gmail authentications to log into the gateway and to use predefined applications. And the gateway itself uses internally things such as robot certificates or identity federations to map the username and passwords to certificates that are required on grid resources. There are more and more gateways that provide mobile-based access, which means that typically it's a redesign of the user interface in order to fit to the smaller resolution of mobile devices. And a recent activity that I just heard about is that one of the Catania Science Gateway Framework instances, the Africa Grid Science Gateway, provides an entry point through Facebook. So in order to use the gateway, you have to go to Facebook, you have to have a Facebook account to log into the Facebook, then search for this Africa Science Gateway portal, and then if you click on the Go to App page, then you are redirected to an identity provider. You can choose from which identity provider you have a username and account, a user account. After you selected that, you log into the portal by providing an extra authorization detail. So I see that someone is joined. I'm going to mute that calling user number 2 and then continue. So this Facebook-based integration is again a nice example of how to make science gateways more easy to access to new communities and how to make the access more seamless to communities without the need for personal certificates. So let's move on to from the grid to the cloud activities that are in EGI, and particularly about the federated cloud system that has been set up recently inside the EGI collaboration. The idea here is that just like the grid was established a decade ago by integrating clusters from different institutes, the idea here is to have a large cloud by integrating local clouds that are provided by different institutes. So the different institutes, resource centers, can choose whatever hypervisor system they have. Currently we support OpenStack, OpenNebula, and some other local solutions, and then integrate these through a thin layer of commonly agreed standards into a large federated cloud, on top of which domain-specific services can sit. The difference here, compared to the grid, is that these services can sit inside virtual machine images, which means that instead of pre-deploying, for example, large middleware services on the sites, a community can create virtual machine images and roll out virtual machine images onto sites as they wish on demand. And the benefit of this is that not only batch processing and file-based data management becomes available. This was the case in the grid. But now with this federated cloud mechanism, basically any kind of service could be incorporated, encapsulated into a virtual machine image, and then rolled out by the community onto the sites. So we are not restricted anymore by what the sites provide. We, as a new community, can choose what we want to access and what we want to use the distributed computing infrastructure for. And this federated cloud of EGI is set up through a federated cloud task force, which started in September 2011. And in the first phase, this task force identified open source technologies and open standards that could realize this vision. In the second phase, after this testbed was deployed, the task force engaged with a few pilot use cases in order to support the early adopters and to collect feedback and additional requirements to refine the system. The second phase also established the first user-facing services, such as the first Science Gateway or portal interface for users. In the third phase that started recently in April, the Federated Cloud Task Force moves towards a production use of the system by stabilizing the services, establishing additional user-facing services, not only portals, but also user tutorials and user support services, to provide a blueprint for resource providers so new resource centers can join and contribute to the federated cloud testbed and to engage with additional use cases. I would like to highlight this last one because that could be relevant for this computational chemistry community. By signing up as a new use case provider, they can start using the sites that are already part of the testbed, and they can define and run and operate virtual machine images on this federated cloud. For further information, please refer to the link which is in the title of this slide, and there you can read about the access procedure and how to apply as a new use case provider. And the portal which is related to this federated cloud testbed is shown on this slide. This is the first portal that provides high-level access to the EGI federated cloud testbed. This portal was prepared by the Italian Grid Initiative. The portal itself is available at the URL which is in the title. And what I'm trying to show here is that instead of defining jobs, instead of finding computing steps, what the user can do in this portal is basically to choose a virtual machine image from a repository and then associate his private identity to this virtual machine image, and then start up the chosen virtual machine image with his own access rights on a remote cloud site. And once that instance is created by the portal remotely, the user can access the content of that image, whatever that content is. In this case, the example shows a domain-specific service that has a command line interface, but it can be just as much a graphical interface that provides a computing simulation, molecular simulation service, or anything like that. So here we are moving away from talking about jobs. We are talking about services that one can create in the form of a virtual machine image, can share that virtual machine image with others, so others can start up services on demand and can configure services for themselves or for third parties. Okay, let's move on to the fourth topic, which is the collaboration and communication services. I see that I'm already behind schedule, so I'm speeding up a bit. What I can provide in this respect are services that can facilitate the exchange of information inside a specific scientific community, as well as between that community and the rest of EGI and the rest of the European research area. We are providing software services that can help the computational chemistry VRC organized. We can provide email lists, we can provide single sign-on service that can manage access to email list and can use to manage access to different other software services such as the document repository, to store files, to store documents, such as a training marketplace, to give visibility of training events, such as the application database where you can register your domain-specific applications, and a requirements tracker where you can keep track of EGI-related requirements you have and can submit requirements to the NGIs to specific technology projects. We also provide support to create content and material, for example, about leaflets, success stories, newsletter articles, and so on and so forth. We can organize events together with you under the EGI annual meetings or under your own meetings. And we can reach out to new communities in different projects in different countries through the EGI champions, through the NGI contact points, NGI international liaisons we have, and through the different online publications we have access to. Concerning the EGI champions, I highlighted that with red. This is a new initiative or a recently established initiative in EGI where we flag representatives from different scientific domains as EGI champions. An EGI champion is someone who has knowledge of EGI and has used EGI in the past or is still actively using EGI. The champion would be the key spokesperson for EGI when it comes to talking to members of that particular scientific discipline. What EGI does is provide training and education for the champions and provide financial support for the travel of champions to domain-specific conferences, workshops, and events where this champion can present his or her own work in the EGI context and give visibility to the use of EGI for scientific use cases. At the moment, we have around 9 champions from different fields of sciences, but we don't have one from the computational chemistry domain. Maybe we need one. That's something for this VT, which is a team project, to decide and maybe delegate someone. At the moment, we are having related activities in the pipeline. We are having webinar program with webinar presentations around different technology topics. For example, yesterday there was a talk about the Catania Science Gateway Framework specifically. We are going to have one webinar presentation about the AMGA Metadata Catalog, and we are organizing different events, for example, in Zurich in June, a Science Gateway workshop, and in Madrid in September, the main event of the year for EGI is the Technical Forum. This slide just shows a nice feature of the software services I talked about on the previous slide. Some of these services, such as the application database, the training marketplace, the requirements tracker, and the grid relational database catalog, has a so-called web gadget instance. The web gadget is basically a customized view of that service in a web frame, and this web frame can be embedded into any website. So what this is typically useful for is that a community, such as the computational chemistry community, can create a customized view of applications or software entries from the application database and create that as a gadget embedded into its own website. So instead of sending people from your website to the EGI application database, you can present content from the EGI application database in your website, and you can make your website more informative with requirements, with training events, with applications and software entries, and so on and so forth. So if you go to that gadget creator website, you can create a customized gadget for any of these 4 services. And the last topic I want to talk about in the EGI service portfolio is the operational tools and dashboards. I just very briefly talk about this. The idea here is that a community can be large and can need customized services that are required to be provided for its members. These customized services can be very domain specific, so outside of the NGI's core competence. It can be, for example, a computational simulation code which is incorporated in some portal interface or incorporated in some workflow system. And what the NGIs can do in this respect is to provide you service registry, service accounting, monitoring, and help desk support for you to operate that service. So the core backbone of this operational infrastructure remains in the NGIs, but your service is running in your sites for your community, and your people can operate and monitor the usage of these services through the infrastructure services provided by the NGIs. And there are 5 types of operational services that the NGIs can provide the computational chemistry community with: a service registry, an accounting infrastructure, service availability monitor, a service discovery capability, and a help desk. One example of these 5 is shown here: the service availability monitor, which basically provides customized views of the different services that are available in the different regions, and red and green provides indicates whether the service is available or unavailable. And this is really the last topic I'm talking about. This is about a new project or a recently started initiative that aims to integrate HPC and HTC resources from the 3E infrastructures, from EGI, from EUDAT, and from PRACE, EGI is basically a cluster-based high-throughput computing infrastructure. EUDAT is a data storage infrastructure for short and long-term storage, and PRACE is the European supercomputing infrastructure with high throughput, with high performance computing sites. And the objective of this pilot project basically is to bring together representatives of these three infrastructures and of three scientific communities. One is the MAPPER community, which deals with multi-scale simulations from different fields of science, including water management, life sciences, and so on. The virtual psychological human and the virtual earthquake and seismology community, and identify common data access and transfer protocols by which workflows defined by these three communities could use EGI, EUDAT, and PRACE sites in an integrated and seamless way. So through the activities, we are going to identify tools and protocols that work well with the middleware that are hosted on these three infrastructures and demonstrate real benefit from the workflows of these three communities through the use of these tools and protocols to access the three infrastructures. Actually, we are having running two pilots in parallel. The first pilot is focusing on the data sharing and uniform data access option. And here on the right side of the slide, you can see the protocols and tools that are tested and set up in this context. And the second pilot is the monitoring and resource discovery capability, which looks at the problem of how to register resources into information systems that could be used by workflow managers in order to identify suitable HPC, HTC, and data resources from three different infrastructures in a seamless way. This pilot project is expected to conclude by mid-August. By then, what we expect is that we will have a couple of tools that provide graphical and/or API-based access for the workflows of these communities in order to transfer data across the three different infrastructures for the benefit of the workflows of these three communities. So the conclusions of the presentation. EGI is based on a federated model. The NGIs are the key resource providers, but besides the NGIs, we have a large number of projects that provide service and support for different users, different types of users. The EGI collaboration provides a well-established grid system and working on cloud infrastructure, which is currently in a pre-production mode and is open for new communities to join. And EGI is not just computing and storage. You heard that there is a human support network from the NGIs with named contact points that are available through the website. There are ready-to-use virtual organizations and scientific application in this infrastructure. There are various porting and application hosting tools that you can use. I talked about workflow tools, workflow integration tools, and science gateway frameworks. We can provide some of the collaboration and communication services so the computational chemistry community can organize and set up itself. And if needed, we can provide infrastructure operation tools and dashboards. So if it comes to operate services for computational chemistry domain, we can help you with that as well. So there are various possibilities to use and extend the EGI services for the benefit of the CMMSC virtual research community. Thank you. That was